Hello, this video starts a long sequence of videos on the area formula, the geometric measure theory version. Let's see where you have last seen this formula. That was back in calculus when you were given a surface sitting inside R3 and you were asked, or you were taught rather, how to calculate its surface area. One way of doing that was if you could describe your surface in terms of a function of only two of the variables. So if you could write z equal f of xy, for example, and that means it's parameterized over its shadow onto the xy plane. And if was nice enough, that means it at least had derivatives, then the surface area of S would be calculated by integrating over the shadow the quantity square root of 1 plus partial of z with respect to x squared and partial of z with respect to y squared. Well, these are just partials of f. And then dx dy. So this is a 2D integral over a flat 2D plane. It makes sense. And the claim is that this is a good definition of surface area. So this is not really a theorem because we don't even know what surface area of S is to begin with. All we've been taught is that just do this and that is the surface area of S. Probably some justification for this formula is given with pictures and if you're lucky with 3D colored animations. What else is true is that you could do this over any other plane. That means if you project sideways onto xz plane, again you have a similar formula. And more generally, this description of your surface doesn't have to be from its shadow. If you have a sitting in R2, so not A, say let's say U is an open set sitting in R2, and f, that is a function going from U into R3, this parameterizes S, your surface. So that means it is injective. You don't overlap, overcover. And this is C1, say continuous derivatives. Then the surface area of S again can be calculated. So you integrate over U. So let me draw a picture of actually where U is. You have a whole new plane R2, and here you put coordinates UV, and U is sitting somewhere here, and F is a function that goes all the way into this R3, and it parameterizes your surface. Every point on your surface is F of some UV for a unique UV. So the claim is that if you integrate over U, derivative of F with respect to U, that will be a vector. Remember, F has X, Y, and Z components in the target. So when you take derivative with respect to U, that means you take derivative with respect to each one of them. And then F of V similarly is a vector in R3. You cross product them. That's only a vector. You don't want to integrate a vector. You take a norm, the size of that vector, and then you do du dv. So you integrate in the external space, which is this R2 with the UV variable names. You integrate over this some object, and the claim is that that object, that quantity you get, is equal to the surface area of S. If you, in your undergraduate calculus, questioned why would this be independent of what F you take from what U, because two different people will definitely come up with two different ways of parameterizing your surface. Why does it not depend on how these are selected? And if you ask that question as an undergrad, then congratulations, you were on your way to discover Riemannian manifold theory on your own. And you're probably not even watching this if you ask that question in your undergrad. I personally didn't, and I'm here, so there is hope. Don't worry if you're an undergrad and you never asked this question. So this is still in the realm of differential geometry. You have nice injective parameterizations with C1 maps. Your space over which you parameterize is an open set, and everything is as nice as you can visualize. The geometric measure theory version of that tosses in measure into it, and that allows a crazy generalization of this theorem. To be precise, it reduces the assumptions on how nice this parameterization F can be. So let me state the coarea formula, and then we can talk about what is involved in it. So I may have said coarea formula because these days I use this word a lot. It's area formula for whole series. So area formula says, suppose F goes from Rn into Rm, where n is less than or equal to m, so it's kind of embedding into a larger space, is Lipschitz. Okay, distance of image is bounded by L times distance of the points you begin with, L independent of what points you pick. And A, a subset of the domain, is just measurable, Lebesgue measurable. It's not a nice open set, it can be a counter set, and whatever other measurable set you can imagine. Then, okay, integrating over A, some Jacobian of the derivative of f of x, which I will define in the next line, dln of x. So this is just a real number, the Jacobian, and you're integrating over a measurable set, all makes sense, equals, okay, I would like to say that the surface area of image of f, so f of a, comparing to the pictures we had above, is some n-dimensional object sitting inside Rm, so we can talk about its n-dimensional measure. It's natural to talk about its n-dimensional measure, and here Hn is the Hausdorff measure. So here we're truly beginning with a notion of area, and then this becomes a true theorem because you want to prove that it is equal to different quantity. Now the theorem as it is actually false because f is not assumed to be injective. And the simplest counterexample to this equality right now is that you have f covering your space, your surface, twice by repeating on a copy of the other set. So that's why we have to include here how many times pieces of your surface get covered. If it gets covered 10 times, you have to calculate that part 10 times. And that is done by introducing the multiplicity function. So here you will integrate this multiplicity function against dHn, the Hausdorff measure of y, over your f of a. So the multiplicity function says if I give you y in the target, how many points from A get mapped to it by f? Okay, now that is a true claim where, so let's write down what these are. Jacobian of df of x equals df of x, the derivative of this multivariable function, is not a square matrix. You transpose it, then you multiply with itself, that becomes a square matrix. Now you can take its determinant, and that is basically the real determinant of df times itself because of the transpose. So you take a square root to take away that multiplication by itself. Okay, that is what Jacobian is. And nf of a y is the cardinality, the number of points x in A, such that f of x equals y. This can be infinity also. For example, if f takes all of A into just one point, then this cardinality is equal to cardinality of the whole set A. So this can in fact be infinity for certain y's. Let me double check. Is everything well defined? Does it make sense? And do we have a theorem? The answer is yes. The claim that this multiplicity function, for example, is measurable, hn measurable, so that this integral makes sense. The claim that you actually have a derivative and that Jacobian is now a measurable function is also part of the claim. And of course, the big part is that the equality holds. So that is the geometric measure theory way of how you compute areas. We have to say that if f is really injective, this is always equal to 1 along fa. Therefore, you can just replace it with 1, and therefore this integral just becomes hn measure of f of a. So it all makes sense. Why do we have a derivative? Why is this object well defined? Is due to the deep and amazing Rademacher's theorem, which says that if f is merely Lipschitz, then it does have a derivative almost everywhere. Except for a Lebesgue null set, the derivative does exist. We will go over all of these that I'm tossing your way in the follow-up videos, of course. That's why we will have a long list of videos. But the point is, my goal in this series is not to just give you an amazing theorem and say this is true, and then provide some hand-waving arguments and pictures and justifications for that. I don't want to make you to believe this theorem is true. It is a theorem, it's in books, it's believable. And sketches are good up to some point. They are, after all, sketches. How do you know the proof really works? So my goal will be to provide as much detail as I can afford and finally have a proof, a complete proof of this theorem. Okay, make sure you subscribe so that you see future videos. For now, make a list of ingredients needed in a proof of this. This video will probably be long, and that will be true for also subsequent videos, because we're talking about serious stuff here, and I just don't want to make 10-minute videos that cover only a little bit. That will be difficult then to put together everything and see where things are going and how they are interconnected. So be ready for longer videos. Watch them when you have the time to completely watch them. And let me know in the comments your feedback so that I can employ those in the future videos that I make. We want to make this really useful and not just something about presenting beautiful math without getting deep into the hard work of verifying theorems. Okay, what will be needed? The first thing we mentioned, the derivative exists, so that will be Rademacher's theorem. Rademacher's differentiability theorem. Okay, I just mentioned what it means. We will need this fact that I proved in my Hausdorff series, and that was that the Hausdorff n-dimensional Hausdorff measure agrees with the Lebesgue measure on Rn. Notice that all the dimensions match here. The third thing we will need, I'm cheating off my paper, will be Sard's theorem. Okay. One thing for the parameterizations that we kind of took for granted is that the derivative of those parameterizations have rank 2. You want to parameterize a surface, you want to move in 2 separate directions. And that is exactly saying that the derivative has rank 2. But in the proof, in the statement of the area formula, we don't actually have any restriction on it. So there will be parts of A where derivative is actually low rank, and Sard's theorem takes care of that part. And Sard's theorem is of interest in its own right, and therefore we will spend some time on this. Linear algebra. This answers the question, why on earth is Jacobian defined that way? How on earth did someone come up with that? And that will be some geometric linear algebra, some beautiful stuff there too. So I will assign some videos just to that, to determinants of linear maps and this Jacobian. Okay. I think that is probably all that we need, of course, plus salt and pepper all the time, which means some measure theory stuff. But the good thing here is that going over this proof and trying to include all the details and commenting or making separate videos about each individual things here will already put you at the heart of geometric measure theory. You will see already in this series a whole bunch of tricks and concepts from geometric measure theory that are then used in many other contexts as well. And finally, some videos will be dedicated to applications of area formula. So I hope you will follow the series, and more importantly, you will tell other people about it, and you will put comments and your feedback. Thanks a lot for this video. I promise I'll be uploading the follow-up videos pretty consistently and as soon as I can, even during this holiday of I will still be working on this project. I have been preparing this project for a long time. I also have been sitting on this for a while, and finally I decided that there is good reason for putting this stuff out on YouTube. Thanks a lot and have a wonderful holiday and enjoy your break.